Okay, welcome to Unit 7.6. Today we're going to complete the fundamental theorem of calculus. So this is part B. We only have one topic to really cover in this. So let's do kind of an exploratory problem to kind of understand the basic premise of this part of the fundamental theorem of calculus. So let's go ahead and evaluate whatever I got up here. So let's read it out loud together. So this says d dx. So what does that mean? This is the derivative of the definite integral from 1 to x of t squared with respect to t. Well, how do we do this? Well, step one, let's go ahead and evaluate just the definite integral. What would that give me? Well, okay, what's the integral of t squared? It's simply going to be t cubed over t. Then I'm going to evaluate it from 1 to x, so that becomes f of b minus f of a, right? So it becomes t cubed over 3 evaluated from x to 1. So simply put, there we have that. And then we can plug it in and we get, if I plug in my x, it's just going to replace all my t, so that becomes x cubed over 3 minus, so f of b minus my f of a. So here's my a, 1 plugged in becomes 1 cubed over 3, or just 1/3. So I finish with x cubed over 3 minus 1/3. But I'm not done, because we've only accounted for my parentheses. We have to account for what's outside of it, and it's asking us to derive this. So here's step 2. Let's go ahead and take that derivative of course, what we just figured out, which is x cubed over 3 minus 1/3. Well, what's the derivative of x cubed over 3? Well, the derivative of x cubed is 3x squared. This is just a constant multiple, so I can leave it. So this becomes 3x squared over 3. Well, my 3's are going to cancel out, and I'm left with x squared. The derivative of a constant value outside here is just going to be 0 because I'm subtracting it. So that's going to become just x squared. Well, let's look at that. We're going to look at that comparison between our original value and our final value. But before we actually look at it, let's look at just one more, see if we can catch that pattern, see if we can understand what's going on. Okay, step 1, we're going to go ahead and deal with that definite integral. Okay, again, here we have a 5 on top, it's attached, and so it's a constant multiple. So I can kind of just leave it alone, I can bring it down with it. Well, the integral of t to the 6 is, we're actually going to be looking at the integral of t to the negative 6. So that becomes 5t to the negative 6 dt. Which is that algebraic rewrite. The integral of that becomes 5t to the negative 5 over negative 5. We evaluate it from 1 to x, or f of x minus f of 1. And so we're going to get negative 1 over x to the 5th minus negative 1 over 5 to the 5th, which is just going to be 3125. That one you'd probably have to plug a little bit into the calculator. But we're not done. We've gotten to this point, cool, but last time we had a step 2. We have to deal with what's outside my parentheses, so let's go ahead and derive this. Well, starting with the right-hand side, the derivative of any constant, even if it's this weird, funky fraction, the derivative of this is just going to be 0, so I don't have to worry about that. We're just worrying about this derivative. Just like before, we do a little bit of algebraic manipulation, so negative 1 over x to the 5th becomes negative 1 times x to the negative 5th. So I can take that derivative, and that derivative gives me, you can't see that. Sorry about that. That derivative gives me 5 over x to the 6 minus 0, so that's just 5 over x to the 6th. Again, let's look at what that pattern created. So we got this derivative of my definite integral just gave me x squared. This derivative of my definite integral just gave me 5 over x to the 6th. So what patterns do you see? What do you notice? Well, if you notice that we simply just took our x value and replaced it with our t, we took our x value and replaced it with our t, then you did what you needed to see. Okay, the fundamental theorem of calculus also tells us, besides f of b minus f of a, it also tells us that if we have continuity, we need continuity, right? If we have continuity, then if our definite integral is equal to this big F, we know that, right? Integrals are typically notated with big F, and has a derivative every point in that interval you're looking at, then the derivative of my integral, which is what we did, the derivative of the integral, right? D of big F, the derivative of my integral, must simply equal f of my x. That's as simple as we can get. We're going to see today, though, that it's not always going to be that easy. We do have to do a little bit of manipulation. Maybe you might see it as use substitution, however you want to see it. We do have to do that. Okay, our first example, very simple, very easy. So, first things first, let's talk about kind of the concept that we're doing here. Am I taking a definite integral from some constant value to my letter x? Then we are in the correct shape for the fundamental theorem of calculus. So as long as it's some constant value to x, so from my a is a constant, my b is x, then all we do is simply replace our letters. So my this new one's going to become the cubed root of 1 minus. I see a t, well, I want to replace it with x. Plus, I see a t, I want to replace it with x. I can't forget the squared, though. Whoa, what did I do? I put my square root symbol on my 1 on accident. That's all we're doing. With something as simple as my a is a constant, and my b is simply x, then all we're doing is replacing x with our letters, okay? Technically, we are multiplying by the derivative of b. Well, my derivative of x, b is my x, right? My derivative of x is simply 1, so we're really just multiplying by 1. Want to double check our work? It's actually on the bottom. There we go. Ta-da! Again, we're going from a constant, definite integral of a constant, to something else. We've got x. Okay, so because of that, we can simply replace. So this is going to become sine, even though it says t, I want to replace it with x, over x. It's as easy as that. Ta-da! Okay. Another simple example. So what do you think we're going to do? We've got e to the negative t squared, but we're going to replace our t with x. So you think it's going to be e to the negative x squared? It sure was. E to the negative x squared. Ooh, what do we do in a situation like this? We have a constant, that's our a is a constant, but our b is not simply just x, it's cosine of x. So what do? Well, we begin the same way. We're going to replace, so we're going to say it's going to be 1 over, instead of t, I replace it with my b, cosine of x. But like I told you in the previous slide, or previous couple slides ago, I told you technically we're multiplying by the derivative of my b value. So what's my derivative of cosine x? Negative sine x. So really we get negative sine x over cosine x, which would be our answer. But you know, we know a little bit of trig, right? We know some manipulation. So perhaps it's smart to be looking at our trig and practicing, because on a multiple choice test, you never know. It might say negative sine over cosine, or it might tell you it's quotient identity from trigonometry. The quotient identity tells me what equals sine over cosine? Tangent. So this becomes negative tangent x. Awesome. I have no idea what answer I put in, which form I put, so we can double check. Oops. I simply left it in its most basic form. That's fine too. All acceptable answers. Okay. Well, now this one looks a little funky. So it's saying, suppose g of x is equal to the definite integral from 0 to x of e to the tan t dt. Then what is g prime of x? Oof, that's a little bit crazy. It's a little bit confusing looking. Let's just break that down very, very, very simply. So g of x is equal to my integral. So what does g prime mean? Take the derivative. So g prime tells me I am taking the derivative of my integral. Is that what we've been doing this whole time? It absolutely is. This is just another form that you can see. This is just another way that they could write it on an AP test, on one of my tests, etc. So we're first things first, we're going to go ahead and replace. Isn't that what we do? So we're going to say e to the tan of x. Well, did I go from a constant, 0? Did I go to simply just x? Yeah. Then do I have to do anything else? No. That's it. We finished. Ta-da! Ooh, but look at this one. I'm going from 2 to x cubed. Again, constant value is a, so we're good there. Don't have to manipulate that. But my b is not simply just x. So like I told you before, now we have to multiply by the derivative of that b. So let's start with replacing. First thing we're going to do is say cosine. Instead of x, I want to write x cubed. But I can't forget that squared. That's part of this. I can't just disappear it. And then I'm going to multiply that by the derivative of x cubed, which is simply 3x squared. Well, we can simplify this right here, x cubed to the squared. Well, any exponent to an exponent, I multiply those exponents. This becomes cosine of x to the 6th times 3x squared. If we're writing it in correct notation, my 3x squared must come to the front. And if I double check that answer, there we go, 3x squared cosine of x to the 6th. Here we have a funky one. This is the first time we've seen where a does not equal some constant value. Well, what do? Well, what is this telling us from x to x squared? This is saying I have some value x squared, and I want you to calculate the definite integral in between. Well, we learned about a property of integration called additivity, where we could split up an integral. Well, how do we do that? So we're going to say some constant value point is in between them. What's the easiest constant value point for me to pick? 0. So we're going to go from x to 0 and then from 0 to x squared. So I would rewrite that integral right there as x to 0 of 1 over 2t dt plus, this is my additivity property, from 0 to x, ooh, that's really close to it, I'm sorry. I'll write it small. Of 1 over 2t dt. I can do this. Again, this is the additivity property of my integration. But what did I tell us? We needed to have it going from a constant value, to b, preferably just x, but some form, something that we're replacing, that's okay. Okay, so this side looks great. We could do that. We could replace. It's not just x, so we'd actually have to multiply by the derivative of this. But what about over here? I'm going from x to my constant value. That doesn't help me. So what we're going to do is we're going to apply another property, and we're just going to flip it. Well, in order for me to flip it, there's something I've got to change about it. I'm going to give you a hint. Something out here I want to change. Right now it's positive. What do you think I'm going to do? All right, I'm going to make it negative. So this is going to become, actually, I'm just going to do this. We're going to erase it, make it a little bit easier on ourselves. This is going to become 0. This is going to become x. But again, if I flip those, I must change the sign. It was positive before, it is negative now. Now I am ready to actually move forward and substitute in my x values and take care of any derivatives I have to take care of. So this simply becomes 1 over 2t plus 1 over 2, oh, why did I say 2? My apologies. We're replacing, aren't we? 2x. This becomes 2x squared, but because this is not simply x like this one was, I have to multiply by the derivative of x squared, so that's actually 2x. We could technically leave it like that. I'm going to go ahead and change my one so we can receive that again. So 1 over 2x plus, 1 over 2x squared times 2x. Okay, so I could technically leave it like that, but you know, we could do a tiny bit of algebraic simplification, some very basics. Well, I've got an x, 2x is on bottom, so I can get rid of 1. I've got x right here, so I can get rid of that. This now becomes 1 over 2x oh sorry, this should have been negative this whole time, my apologies. Negative 1 over 2x plus plus 2 right here over 2x. Now some of you might be asking, well, why didn't you simplify this? Well, because we have common denominators, so it's already set up for me. I can just go ahead and deal with this fraction. Well, 2 plus negative 1 is simply going to give me 1 over 2x. Yeah. Okay. Again, here we have another one. There's a little something missing up there, I suppose, a little typo. There should have been a dx. I'm short, can't reach quite that high. Or it should have told us that, you know, f of x is going to equal this, find f prime, or h of x is going to equal this, find h prime, something like that. Should have let us know, otherwise we were doing a straight definite integral, and that's not what we're doing today. So, first things first, let's go ahead and substitute. So instead of s, I'm going to write the square root of x. I can't forget my squared. The square root of x, I can't forget my squared, plus 1. But square root of x is not simply x, so we have to take the derivative. Well, the derivative of the square root of x is the same as saying the derivative of x to the 1/2. I apply the power rule, and this becomes 1/2 times x to the negative 1/2, which is the same as saying 1 over 2 square roots of x. So I'm going to multiply by 1 over 2 square roots of x. Again, we can do a tiny bit of algebraic simplification. Well, if I square a square root, does all of that cancel? Yeah. Okay, so I'm just going to be left with x and x. So this becomes x over x plus 1 times 1 over 2 times the square root of x. Again, if I want to double check my work, I sure can. And boom, same exact answer. Alrighty. Again, we're back to a little bit of trig, so first things first, let's make it easy on ourselves. Just start with the replacement. Before I can replace, I gotta check, is my a constant? Yeah, then we're good, because that just means it's gonna become 0. I don't have to worry about it. So, this is gonna be, t is gonna become cosine of x, and then times cosine, that's still from there, and that says t again, so cosine of cosine x, it's cubed, so my cubed is actually going to be on my cosine. But again, I'm not done, because I have to multiply. I've done the replacement step. This t became this t became this, and I cubed it because it's already cubed, but I'm not done. I have to multiply by the derivative of my b, so this becomes, the derivative is negative sine x. So if I put that across, that becomes negative, I'm gonna write it like this, cosine x sine x, and then I'm just gonna put that like this, times cosine of cosine cubed x. Woo! That's a funky looking one. Alrighty. This implies that there was simply an x, and that's not what we had. I don't know, this is all crazy. That's an incorrect answer down there. All right. Well, here we have, is my a constant? No. So, but is my b a constant? Yeah, so what are we doing here? We're not going to do additivity. We're not going to split it up. What we're going to do is we're going to flip it. So if I flip it, I have to change the sign. So this is actually going to become negative of the definite integral from 17 to tan x of sine t to the 4th dt. Well, now I can apply and I can sub in. So this becomes, I'm going to write sine, t is going to replace with tan. Tan is actually to the 4th power, so I want to make sure my 4th power doesn't go to my x it goes to my tan. Am I done? Not quite. Because this is not an x, I have to multiply by the derivative of it. The derivative of tangent is simply, let's do this, secant squared x. And let's check if that answer is correct. That one, you know, it's going to be checked. I forgot this negative. This negative is here, and I did not bring it down. So the answer would have been negative secant squared x sine of tan to the fourth x. Whew, that one's a mouthful. All right, this is technically your demonstration of learning, but I'm going to go ahead and go through some of these example problems so that you can get to the worksheet. So if this tells me that given f of x, a big F of x is equal to this definite integral, then I want you to find the actual f of x. So how do we do that? Well, we have to integrate. This is simply solving a definite integral, isn't it? We have to integrate. Well, the integral is going to become 1/3 times, I'm going to actually do t to the negative 2, so that becomes t to the negative 1 over negative 1. That just becomes negative 1 over t. Is that good? I think so. I believe so. Okay, so then I evaluate this from 2 to x. So then I'm going to plug in my f of b, so negative 1 over 3x minus negative 1 over 3 times 2, which should give me negative 1/3 x, negative 1 over 3x, sorry, plus 1 over 6. I think that's good. I think that's correct. Yeah, this is just a math manipulation, so if we wanted to see how we got from here to here, this top part becomes negative 1 over 3x negative plus 1 over 3 times 1 over 2. This is actually times 1 over x. And we can pull out those 1/3, and this will be 1/3 times, and we're going to just switch these, so it becomes 1/2 minus 1 over x. Ta-da! Well, now it's not asking you to figure out, excuse me, now it's not asking you to figure out f of x. It's actually asking you to sub in a real value, f of 2. So if we look back, all we're doing is plugging in our 2 right here, so it's going to become 1/3 times quantity 1 over 2 minus 1 over 2. So this is all going to become 0. 0 times anything, it's simply 0. So if I want to double check that work, there we go. Here we go. I plugged in my 2 and I got 0. All right, well now here we're talking. This is our fundamental theorem. So given this same information, what is f prime? Well, again, we are taking the derivative of a definite, of my integral, so that means I should just end up with my original function, but we're replacing it with the letter value x. This becomes 1 over 3 x squared. Simple as that. There we go. Again, it wants us to fill in that value, fill in a 2, plug in 2. So 1 over 3x squared is going to become 1 over 3 times 2 squared, which is 4 and 3, which gives us 1/12. Very good. And before we continue on, so we finished example 3 and I'm going to move on to example 4. Before I actually continue on, let's do a tiny bit of review of the relationship between f prime, and f double prime. Okay, so if I have this table, f prime, f double prime, well, what do we know? Okay, well, when f is 0, aren't those the roots? When f is positive, then it must be above the x-axis. And it must be below the x-axis if f is negative. Okay, we know that. That's algebra. That's looking at a graph and figuring it out. Well, what happens in that first derivative? We know the first derivative tests for increasing, decreasing. But what do we call this? When f prime is equal to 0, we call those critical values or critical points. And we know that this means it's possible, it's not, we don't know for sure, but it's possible extrema. The only way we can determine for sure is to test it. Okay? What happens when f prime is positive? Well, when f prime is positive, f is increasing. When f prime is negative, f is decreasing. So again, when f prime is above the x-axis, f must be increasing. F prime is below the x-axis, f must be decreasing. What about with f double prime? When f double prime equals 0, what do we call those? Points of inflection, right? These are possible values where concavity changes. Well, when f double prime is positive above the x-axis, what does that mean? Well, when f double prime is above the x-axis, f must be concave up. And so, therefore, this must be concave down. Okay, so let's kind of remember that, jog our memories from before. And then one more little thing I want us to explore is, well then, if these are the relationships between f prime and f double prime, well how would we look at our relationship between our function, our derivative, and our integral? Well, that's simply put just going to be, if this is our function, well then our f prime is going to knock it down a peg, and our integral, our big letter f, is going to bring it up a peg. So we can actually look at that and say, okay, so we can look at these relationships and say, yes, we know our function and our integral would be this, but what happens if we're given other information? That's what we're going to see in this example 4. What I mean by that is, you know, like if I was given a graph of, what am I trying to say? If I know an integral, its derivative would actually be the relationship between f and f prime. You know, we have to think about that, right? Like, I guess I should have written this backwards. Let's write it the other way around. There we go. So if we're looking at an integral, its derivative has to be the relationship between f and f prime. If we're looking at an integral, its derivative would be the function, but the second derivative would be that d dx, and that would be the relationship between f and f double prime. Okay, so example 4a, we are given some graph, and in fact we are given the graph of f, okay? It's our function f. So again, I'll say that again. This is the graph of f. This is not the graph of h. This is the graph of f. So let's declare what that relationship could or possibly is. Well, if h is equal to the definite integral of f, then what's that relationship? Let's go back to this. F, big F, and f prime. Okay, so if we have to think in these terms, I realize that still says f, and that might confuse us, but if some function's integral is h of x, so that means this is my hx, right? So that's the function, and any derivative there beyond would be f prime. So what is this relationship? F prime, and f double prime. So that's the relationship we're going to explore. Okay, so the first thing it's asking us is to figure out what h of 2, h prime of 2, and h double prime of 2 is. Well, h of 2 is simply my integral. Well, that's very simple. That becomes, I simply plug it in. So h of 2 is going to be equal to the definite integral from 0 to 2 of f of 2, all right? Or sorry, f of t, and my f of t is right there. So let's look at it. From 0 to 2, did I create any shape? Because isn't that what we're doing? Definite integral, area under the curve. Yeah, I created a triangle. Base of 2, height of 1, so 2 multiplied by 1/2, which is my area formula, gives me simply 1. So I know that h of 2 is going to equal 1. Then h prime of 2 is the derivative of the integral. The derivative of the integral is just my function. So what's my value at 2? 0. h double prime, so that's the integral's second derivative, is simply the original function's derivative. So the original function's derivative, my derivative is my slope. Well, what's the slope right here? This is a line, a linear line, that actually has a formula of y equals negative 1/2. Isn't that my slope? Down 1 over 2, down 1 over 2, negative 1/2 x plus 2. So that's a linear line. My only slope right there is going to be negative 1/2. So my h double prime has to equal negative 1/2. So if I want to double check those answers, h of 2 is 1, h prime of 2 is 0, and h double prime of 2 is equal to negative 1/2. We're good to go there. Okay, let's look at our next question. For what values of x in the open interval from negative 2 to 10, so that's our entire graph, is h increasing? Oof, that's tough. We got to think about this. What is h? H is my integral. To figure out if something is increasing, I need to look at a function's derivative, right? Derivatives tell me that. So again, I can write it for you again to tell you that relationship. So we see f is our integral, f and f prime. So again, we are looking at h, and we want to know if it's increasing. So do we look at our function? Yes. Okay, so to figure out if h is increasing, my first derivative test tells me that my first derivative has to be positive above the x-axis greater than 0. So where is my function greater than 0? Because my function is my first derivative test. So where's my function above the x-axis from the interval negative 2 to 10? Well, here, from negative 2 to 2, and from 8 to 10. And I think when I wrote this, when I was writing this, I think I only saw the right-hand side. I didn't catch the left-hand side. My apologies. But it doesn't just end there. It says, explain your reasoning. Well, what is our reasoning? Well, it must be well, let me add this on. There's also an interval from negative 2 to positive 2. So, from negative 2 to 2 and from 8 to 10, h is increasing on these intervals because f is greater than 0. If we were looking at our unit 4 or 5, where we actually looked at our first and second derivative test, this would have said f prime is equal to 0. But again, remember, if we are given certain graphs, we have to act that way. So we have to write our justification in terms of what we're given. We are given, this is our graph of f prime, but they are calling it f, and they are calling the original function h. So we have to write it as f is greater than 0. Okay, now it wants us to find any x-coordinate point on the entire interval where we have a point of inflection. Well, a point of inflection is my second derivative test. Second derivative has to be equal to 0, and it can't just be equal to 0, and it has to go from above the x-axis to below, or below the x-axis to above. You have to have a change in concavity. But we aren't given the graph of the second derivative. We're given the graph of the first derivative. This graph is our first derivative. So what do we have to know? Well, we have to know that if it's going from increasing to decreasing, right? Where it is going from increasing to decreasing. So what does that mean? Slope, right? So I'm going from increasing to decreasing. Do I also need to know where it's going from decreasing to increasing? Yeah, that's also a change in concavity. So decreasing to increasing. So I have an x value at 0, and I have an x value at 6. So at 0 and 6, but we need a justification statement. There must be points of inflection at these points because f, again, justify with what we're given, f goes from increasing to decreasing and decreasing to increasing, or vice versa. All right, our next question says, for what values of x in the open interval, negative 2 to 10, again, the entire graph, is h concave down? Again, we're looking at our second derivative test. So to determine concave down, f double prime, my second derivative, must be below the x-axis. But we aren't given the second derivative, we're given the first derivative. So what do we have to know? It just has to be decreasing. So where is it decreasing? Well, it's decreasing from 0 to 6, that. And so there we go, 0 to 6, here's our justification. H must be concave down on this interval because f is decreasing, okay? I think this is our final question. Find all values of x where h attains a relative max. Ooh, relatives max says, where do we get extrema from? We know that we have our first derivative test, we have our second derivative test. Second derivative tells us points of inflection, which is changing concavity, and it tells us if it's concave up or concave down. Well, the first derivative test tells us if the function is increasing or decreasing, but it also tells us those critical values, and critical values tell us possible extrema. Is maximum my extrema? Yes. The only way to determine if I have a real max is if it's going from increasing to decreasing. So, to figure out if my function is going from increasing to decreasing, I have to look at my first derivative's graph and figure out if it's going from above the x-axis to below at any point. Is it doing that? Well, heck yeah, it is right here, from above to below. Why don't I care about this point right here where it's changing across the x-axis? Well, this is going from below to above, so that means it's going from a decreasing to increasing. That's not a max, that's a min. That's a valley, that's not a hill. So the only point we have is right here at 2. We have a possible relative max, so we have a relative max, and our justification would be there must be a relative max here because f goes from positive to negative. Or you could have done, x goes from greater than 0 to less than 0.